Hello, everyone. I know you are super excited with our speaker today. I see a lot of EC330, EC464 students here. Fantastic. Thank you for showing up. Well, please join me in welcoming Professor Jeffrey Lang from MIT. He did all his degrees, bachelor's, master's, and PhD from MIT back in 1980, and then he joined the faculty of MIT in 1980. He is now the VTC Professor of Electrical Engineering, and he served as the Associate Director of the MIT Laboratory for Electromagnetic and Electronic Systems from 1991 to 2003. Professor Lang's research interest and teaching interests focus on the analysis, design, and control of electromechanical systems, with an emphasis on rotating machinery, micro-nanoscale sensors, actuators, energy converters, flexible structures, dual use of electromechanical actuators as motion and force sensors. He has written over 300 papers, holds 12 patents in the areas of electromechanics, power electronics, and applied control. He has written 2 books. One is on foundations of analog and digital electronic circuits, and the other one is on multi-wafer rotating MEMS machines, turbines, generators, and engines. He's a fellow of IEEE and a former Hutch Foundation fellow. And I can go on and on and on. So I'll cut this short. So it's an honor for me to host Professor Jeffrey Lang from MIT. And one of the things from my personal note back at MIT is he's one of those fantastic teachers whom you look up to and say, one day I'll be a teacher. So please I'll have a Jeff here, but before that, I would like to invite Professor Pete Sauer to give this honorary plaque to Jeff as a token of appreciation for his coming to UIUC all the way from MIT.
Hey. First time here.
Thank you, Pete.
You're welcome, and thank you. We don't get distinguished people that often. But this is a little something. Our department head was in D.C. today talking about cybersecurity for the grid, so he couldn't make it. But if he was here, he would be giving that to you. So.
Well, thank you very much.
You're welcome. Thank you, Jeff.
So thanks, Professor Sauer. So Jeff, it's all yours.
Okay,
and
sure.
I'm sure you will be excited to hear this talk.
Is my microphone on so that everybody can hear me? Yes, great. Okay. So I thought that to open the talk today, I should say just a few words about myself to put this presentation in context. My work is mostly grounded in electromagnetics and electromechanics, meaning energy conversion. And it mixes in power electronics and applied estimation and control when the need arises. Central to all of my work is applications. I think applications are very important. They are a source of motivation. They're a source of targets, things to which you can aspire in your research. They're also a lot of fun, and people take notice of the applications more than they do the general theory, I think. Applications, as I said, are very important to me. Most of them lately come from the micro and nano world, although I've worked on large things as well. And here's some of them that I've worked on in the past. Now, from all of these, I chose today to speak about relays, something as simple as a switch. And in the context of MEMS devices, and that's micro-electromechanical systems, and NEMS devices, nano-electromechanical systems. One, because I find them really challenging and a lot of fun to think about. But two, because they are an example out of my MEMS, NEMS sort of research that spans all the way from the highest power that one might think of for a MEMS device to the lowest power that one might think of as in a NEMS device. And I thought the contrast of the two might be interesting, and also the similarities between the two. So with that, let me start at the high power end and offer an application which has driven a lot of our work. And that application is a residential circuit breaker, which I think is a particularly honorable goal to set for a MEMS device. And here's a picture of a residential circuit breaker. If you own a house, you own a lot of these. Just in brief summary, it's a device that can carry 10, 20, 30 amps when it's closed. When it's open, it'll stand off maybe 600 to 1,000 volts. It's capable of interrupting a short circuit current of 10,000 amps, and it will do this all for $4. And the fact that it can do it all for $4 doesn't leave much room for a competing technology such as MEMS. But nonetheless, hear me out. I'd like to dig into the details of how this device works, and then in sort of the same spirit, how our MEMS devices work. And in doing that, I'd like to point out just a few key features of a residential circuit breaker. The most important thing is the contacts. I don't know if you can see them, but they're shown. Here's one contact and here's the other. This is in the off state of the circuit breaker, and there's about a centimeter separation between the two. They come together to close the circuit. The next thing that's important is the suspension, which holds these contacts and moves them around and makes the travel possible. Importantly, the suspension is bistable, so it doesn't lose its state if the power goes out. If it was open before the power goes out, it's open after the power comes back and closed and so forth. So bistability is an important property of this device. Then there is a pair of forcing springs. One is to provide a large force when the contacts are closed, up to 2 newtons. That's sort of half a pound. And the other is to rapidly open the circuit breaker. And then finally, there's the actuation mechanism. There are two in a residential circuit breaker. One is magnetically actuated, and that detects the short circuit current. And then the other is thermally actuated, and that detects the overload condition that might persist for a while. And finally, there's the package. But in the style of being a good academic, I'm going to ignore the package, which is sometimes the most important part of the system. Okay, so as I said, $4 doesn't allow you much room for competition. But I'll point out that modern residential circuit breakers now are beginning to show or beginning to require that they implement additional features, and in particular, various forms of arc fault interruption. And so this is to detect arcs that occur from line to line to ground, or if you have frayed wires that are arcing in line. Those are all now required in many rooms of the house, like bedrooms, playrooms, and so forth, where people spend a lot of time. It's written into the electrical code. And to carry out arc fault detection requires sensing and processing. It requires silicon, which wasn't in the original implementation of the residential circuit breaker, which I showed before. And as a consequence, whoops, excuse me. Oh, go backwards. As a consequence, these advanced fault detectors now are $30 for 15 amps. So they're 10 times more expensive. And this now leaves some room for competition. So here's where the story begins. About a decade ago, some folks from ABB came to us and asked, could MEMS become a disruptive technology for the solid-state circuit breaker, sorry, not solid-state, for the residential circuit breaker industry? It's a $2 to $5 billion, depending upon how you want to count it, industry in just the US. It's a whole lot bigger worldwide. ABB has a large component, a large share of that industry, and they wanted to know whether they should be concerned and challenged us to do our best to build a residential circuit breaker out of silicon. The idea being that silicon is the material into which they could then put the signal processing that would be required to do the arc fault detection and not have to assemble at the same time the 40 pieces plus the hybrid silicon processor. So that's the challenge that we were given. And I'm sort of showing you here the punchline. This is not of the size scale of a residential circuit breaker. This device from end to end is only about 4 millimeters, but it's got all the components of a residential circuit breaker minus the sensing and control. This is a crossbar set of contacts right here, contact 1, contact 2 being shorted by this crossbar. This device will withstand 1,000 volts. It will carry up to 3 amps, not 10, but we're getting close. The double beams here provide bistability, and we happen to use electrothermal actuation. It's not the sexiest of actuation. It's a little bit slow, probably too slow for a residential circuit breaker, but give me time and I'll try and convince you that alternatives are possible. Anyway, this is the punchline. It is built as a cookie cutter device. By that I mean a single etch into a silicon wafer carves this structure out just like a cookie cutter would carve out of a rolled cookie sheet. So it's very simple to fabricate. It has only one part to assemble. You're looking at it, minus, of course, the processing that's required to put in the circuitry that would do the sensing and control. And some of the interesting statistics are over here. And so now what I'd like to do is carry through some of the invention in science and engineering that went in to develop this device and come out the other end with a prognosis for the suitability of a device like this in a residential circuit breaker. And if you think back to my beginning statement of the fact that a residential circuit breaker is sort of an honorable challenge for a MEMS device, people wouldn't normally associate MEMS with controlling tens to hundreds of amps and thousands of volts. Yet I do believe that it's possible. Okay, so before I move on, probably some of you are thinking that, well, if you're going to use silicon, why not a solid-state circuit breaker? Why not just use some MOSFETs and so forth and build the device very easily? In response to that, I would quote a couple of statements out of the National Electric Code. Basically, that solution is outlawed. In the wirings of homes in this country, at least, open circuits are required in order to break a circuit. So a solid-state circuit breaker is not a legitimate solution, hence the interest in MEMS. Okay, let me move on. Semiconductor switching is not permitted by law. Okay, so let me start first with the suspension and take a look at a few of its characteristics. We want from this suspension bistability, we want the large force, and if possible, we'd like it to have a hair trigger. When it comes time to make it release and snap open, you'd like a minimum amount of actuation force to accomplish that. And the traditional way of forming a bistable device in a MEMS system is with built-in internal stress. And the way that's done, if you could imagine that this is a business card, it's not, but if I were to take my fingers here and squeeze on this business card, it would bow to one side or the other. I'm putting internal stress into that business card and asking it to change its shape. Then if I were to push on it, it could pop through to the other side. And so that's a form of bistable mechanism which is developed by putting internal stress into the originally straight fabricated piece of silicon. And this could be done with 2 layers of material. It could be done through implantation and heat treatment. It could be done in a number of ways. But from a production viewpoint, this is very difficult to control, at least on the MEMS landscape. As I said, you'd like to have a hair trigger, and if the strength of that hair trigger or the hairness of that hair trigger is not controllable from a fabrication viewpoint, then it's not a good solution. So we needed to come up with something else, and here's what we came up with. We start with a beam that is fabricated in this shape. Now this beam is going to snap down from being at a high point here to a low point down here. So right away we're etching in half the stroke of our bistable beam. If we want a centimeter stroke, then this height here above the center line has to be a ½ centimeter. Now if you were to take this beam and push on it in the center, it wouldn't go down flat. That's got too much compressive strain in it, but instead it would assume this shape right here as it pushes through the middle, and you could push it to the other side, in which case it takes this shape but now down below. Unfortunately, if you were to let it go, the energy well, which you might hope that you've put it into, isn't a well at all. This second mode, the presence of this second mode, would allow the beam to pop back up to the other side, and it's not bistable at all. So if you release the force, it will bounce back. And now here's a key insight which my doctoral student had at the time. The second mode differs from this first mode by its shape, its slope here at the center. So what would happen if instead we took two double beams right here and clamped them together so that as the structure was pushed through the center, it was not allowed to have a slope. It then would take the shape of the third mode as it goes through the center. And if you'll notice, that third mode has no slope here. It has no slope, as does this. The third mode is, fortunately, bistable. And so this whole structure snaps through and becomes stable on the other side. Now, there's a couple geometric requirements involved. This apex height here divided by the thickness here has to be greater than 2.31 for some conditions that are based on Bernoulli beam bending theory, which I'm not going to go into here. But as long as you adhere to those dimensional constraints, the structure is bistable. And to give you an example of that, we can look at the behavior of this device sort of in slow motion. You'll see the probe tip pushing down, and it snaps through. There's the bistability, which actually you saw in the very first time I showed the relay. And then we'll scan side to side. So that you can see that it was just a very simple cookie cutter etched beam, which is bistable. So this provides one of the features then that we need for the relay, a bistable suspension. Now for this suspension, again using the beam theory, we've come up with a very simple model for its behavior. Its force displacement curve looks something like this, and we have some design equations down here for what is the force at the top of this peak, at the bottom of this peak, for these zero crossings and so forth. And here are the design equations I've listed down here. They're relatively simple. If you compare them to the experiment, let's see, experiment's right down here. The experiment in the jagged line versus our theory in the dashed line, you'll see that the two are fairly close. So these simple design equations we can use to tune up the shape of the bistability. As fabricated, the device would fit here, and then if you put a force on it, this F, you will start to deflect it in this direction, up this curve. You reach a peak force, and then the force gets less and less and less as you now push the beam through the center. And then on this side right here, it would snap through and come to its final resting point over there. So here's the other bistable resting place. This peak is necessarily smaller than that one, and so this is where you would want to put the contacts. At the high force end, you'd like the resting point right here to hold the contacts closed. Now, I'll point out, and this is important when we get to actuation, that if you take the beam, instead of having it just absolutely straight across, but if you were to tailor its shape, and I've got an example of this in a little bit, you can make the height of this arbitrarily small. So this force at the bottom of the curve can be made arbitrarily small, and that's the hair trigger, because it's the force you need to apply to start from here and go over this peak that is what kicks the beam back to the other side and allows you to open the contact or close the contact. Okay. So could this be used for a residential circuit breaker? I need to give you one more piece of information, and that is the maximum strain inside the silicon. We don't want it to break as we move this beam back and forth. But if you take the strain equation and that maximum force equation, set the maximum force to 2 newtons, and work your way through this one design equation here, what we find is we can meet all of the specifications with a bistable beam, which is surprisingly close at 6.3 millimeters. Sorry, that should say 6.3 centimeters, my mistake. 6.3 centimeters, which is the size of a residential circuit breaker. So very luckily, a silicon bending beam would provide all the requirements of the bistable suspension in terms of force, stroke, and hair trigger quality that the multi-component device used as the ordinary residential circuit breaker. Okay, so now let me move on to another topic, and that is actuation. I showed you in the very first view graph that, or maybe the third, that we could build an electrothermal actuator, which would nicely move the relay back and forth. But electrothermal actuators are inefficient, and they are not very fast, so you would like to be able to interrupt that 10,000 amps very quickly. What would be much better is an electrostatic actuator, because it's much more rapid if you can provide the force. Now, the normal method of providing force for an electrostatic actuator is to close a pair of gaps, but that does not have a very long, that does not offer a very long stroke, and we need an actuator, an electrostatic actuator, with a modestly long stroke so we can push the bistable mechanism over its potential well off to the other side. So those types of actuators won't work. So we relied on a different one, which is called a zipper actuator. And the way the zipper actuator works, here's the actuating beam right here in the center. And what happens is you apply a voltage between this beam and this beam, and the gap being narrower here causes this beam to bend down, and it comes into contact. Now, between the two is a thin layer of silicon dioxide, an insulator, so the beam doesn't short out. But then the field strength builds up to be very big right here. And then the beam continues to zip along as it continues to close and close and close on itself. And as it does, it begins to impart a force on this catch right here, and it ultimately forces down on this edge, thereby affecting a very rapid actuation, but with a long stroke. The stroke from here to here can be quite long. And you're seeing a zipper actuator work right here. It's a little hard to see it because we can't even catch it in one frame, but the beam that's doing the zipping is this beam right here, and there's another one on the other side. We have a bistable mechanism on the bottom, which happens to have a break in it right here. But you can see also that it's been tailored. It goes from thin to thick to thin. That's to make the bistable beam a hair trigger. Anyway, this is not the end of the story, however. In a cookie cutter etch of a silicon wafer, typically you have a limited aspect ratio. So if you want to etch, let's say, through a 900 micron wafer, as we do, you must suffer a blowout of about 1/10 of that 900 microns. That's 90 microns. 90 microns is a very big gap right here in which to develop any sort of electrostatic force with a small voltage. And so it's necessary somehow to get this thing started. And here's where the invention came in. This little freestanding cantilever out here, which we call a compliant starting zone, at a very low voltage, it's so long that at a very low voltage, it bends up and reaches up upon actuation of this electrode right here. It reaches up and closes the gap way out here at just a very few volts, and then the whole thing zips along like this. So without this compliant starting zone, the zipper actuator couldn't start. But with that compliant starting zone, we can have almost as big a gap in this interior as we wish and still get the thing started on just a few volts. So this is the complete zipper actuator, which we ultimately used in our final designs. Now again, we have some relatively simple design equations for this. The beam has to be long enough to zip, that is to pull in and then start to zip along. So it's got to be flexible enough at its beginning. And we also need that required force to get over the energy well. Now the energy well here I've picked at 1 Newton, which is half of the 2 Newtons. And this is much greater than what is actually required. For these design equations, we can come up with a required length and then a design requirement on the combined thickness and width of the beam, and out comes this design right here as an example. Again, the 6.3 centimeters is perfectly adequate if we combine 6 actuators for this very large force and use 150 volts, which is the rectified, or close to the rectified AC in a residential system. So we now have a bistable beam and a means of actuating it. The last thing that I'd like to talk about are the contacts. So here's a little picture about how we have built our contacts. The early contacts, we used a straight edge sort of contact opening and closing like this, which was cut with the same cookie cutter etch. And then we would evaporate sort of at a very steep angle, a thin layer of metal on the sides, and then electroplate out to make a thick a contact. And that has problems. It gives us a rough sidewall planarity so that inevitably the contacts touch down at a single point. You don't get a good spreading of the contacting over the contacts. And in general, you get poor metallization. You can't get a thick metal layer like this to absorb the incoming energy if you had to, say, dump an inductive load into the contacts. So we invented a different type of contact, which relies on etching with sodium hydroxide. Sodium hydroxide attacks silicon, leaving 111 planes open, and leaves us with almost atomically smooth surfaces that look like this if you wet etch the silicon. And this has a very nice feature. The contacting edges, this one here and this one here, are now sort of open face to the outside environment, so that if you metallize them by evaporation, you can put on a much thicker layer of metal. And furthermore, as the relay closes, it's possible that as they come together, the relay contacts will actually slide along one another. And that's called scrub. It cleans the oxides or the environmental dust, dirt, whatever, off of the contacts and keeps them in good shape. So this, to us, we thought would be a much better contact. It turned out that it was. So we graduated, in a sense, from the early contacts right here, which were the simple crossbar, to KOH contacts right here. It was at this point we decided we better get some understanding of contact physics at the MEMS scale. All of the literature was for much larger scale contacts, and so we built a device that looks something like this to do contact measurements. The whole device is here. You can see there's, I think, 8 zipper actuators on one side, 8 zipper actuators on another side. They all grab a central spine and standing on these crab leg flexures here, and that spine drives this crossbar relay contact into the 2 contacts down here, and here you can see it moving. Importantly, we took out the bistable measurement because we wanted to be able to apply an arbitrary force on the contacts and look at contact resistance as a function of force. And if the bistable mechanism were in there, it would overwhelm the force of the actuators, and it'd either be on or off, and you couldn't look at anything in between. So we took the bistable mechanism out and used the zipper actuators to apply arbitrary forces here, and then began to study contact theory. Here are some results. The Holm Maxwell spreading resistance gives the resistance here as a function of the contact area and a resistivity. And the contact area, I'm calling this the electrical area and this the mechanical area, is also a function of the hardness and of the applied force. And if you put these 2 equations together, you get these straight lines here for different materials, which say how the contact resistance should depend on contact force. The resistance should decrease with the square of the force. With the square root of the force. So you see 1 decade of decrease in contact resistance with 2 decades of force applied. And we saw that dependence in some of the data that I plotted here for different materials. But if you'll note, the green dot's not on the green line, the red dots aren't on the red line, the black and the blue aren't on the black and the blue, and so forth. The contact resistance was inevitably higher than what it should have been from the Holm contact theory. So what we concluded was that probably there is a poor contact due to surface roughness and also possibly due to contamination on the surface. So instead, what we did was to plot the data. We converted this into the mechanical area and this into the electrical area and replotted the data looking for a difference between the electrical radius and the mechanical radius of the contact. The idea being that the electrical radius is smaller than the mechanical radius because of contamination that might be on the surface. And sure enough, this is what we found. This is a line of the two areas being equal. This is a line of the mechanical area being 10 times the electrical area. This is a line of the mechanical area being 100 times the electrical area. And what you see is that for a given material set with its different contaminations and so forth, the plots typically lie on a different ratio of mechanical to electrical areas. And we attribute this in part to surface roughness, but more likely a surface contamination. So this is a first hint that maybe the scrubbing isn't working the way we'd hoped that it would. Nonetheless, we moved on, and knowing now what are the sizes of the mechanical and the electrical areas, which are by, in this force range, well, the equivalent of this force range here, we would have expected them to be around 10 microns or so. We went looking into the contacts to see if we could find those contact points, and we could find regions of contact of the size scale of 10 microns. And I'm hopeful that this picture will show up for you. But here is, for example, a contact spot on an otherwise clean electrode showing that all of the conduction was taking place here. And here's a 10 micron bar, and this is probably, about 40 microns, 50 microns wide. And so that kind of confirms our theory. My suspicion is that this is wider than the 10 microns because one time it hit one place, blew it out, another time it hit another place, blew it out, kept on blowing it out until the mechanical area was happy with the deformation, and then that's where we would, that resulted in a little bit bigger area. And this is the same sort of story, another region blown up in a different relay, and this is only a 2 micron bar, so this one is probably 20 microns wide or something like that. So the thought that we have a mechanical area on the order of 10 to 20 microns, but an electrical area on the order of 1 to 2 microns is I think, borne out by these pictures. Okay, so I should also point out, if I were to go back a few slides, these forces were only with a few millinewtons, not the 2 newtons, which is used in a real relay. But if we were to go back and use the and again, this device is only a few millimeters by a few millimeters, not 6 millimeters by 6 millimeters. But if we were to expand things up to the 6 millimeter by 6 millimeter, what we find is that the home contact theory predicts that this relay should be competitive with the residential circuit breakers, which are typically built today. And just one other thing, we did do some hot switching experiments, which is very important. Hot switching means can you turn off currents can you turn off the relay when the currents are live? And the answer is always yes, if there's no inductance behind that current. There's no energy to dump into the contacts. So what the real question one should ask is how much energy can you dump into the contacts and have them survive? We were up to almost a millijoule in some experiments, which again, if scaled up, would probably mean that these relays would survive a very short circuit fault of on the order of 1,000 amps with typical wiring inductance behind them. That we never actually proved experimentally, but the numbers bear it out. Okay, so just in quick summary here, on the scale of milliamps up to 10,000 milliamps, this is 10 amps where we would like to be, and 600 volts, this is where we would like to be. At school, we've had a couple of different relays, one operating, and these are all at the 4 millimeter scale, one operating here up at 1,000 volts and 1 amp, and one operating down here at 200 volts and a couple of amps. And again, on the 4 millimeter size, it's not hard to imagine, I hope, that if you were to scale this up to 6 centimeters, that MEMS actually could be a disruptive technology for the residential circuit breaker industry. But in the end, it wasn't adopted by ABB, and I should tell you why. It's all economics. The premise in the beginning was that we would put the silicon signal processing onto the same silicon, or the signal processing onto the same silicon from which the from which the residential circuit breaker was fabricated. But that immediately dilutes the density of the signal processing. Now, instead of having many, many circuits per area consumed by one residential circuit breaker, you've now only got one. So you made the circuit more expensive by a factor of the area of the residential circuit breaker divided by the area of the circuit, and that's probably 100 to 1. So inadvertently, we would have made the expense of the circuits 100 times more expensive. They are what dominate the cost of the circuit breaker. That's what took the $4 to the $30 or $40 in the first place. And so from purely economic reasons, as a technology, it didn't make sense. But nonetheless, we did at least prove out, I believe, that MEMS could handle the needs of a residential circuit breaker, which is actually a remarkable statement because because we don't typically think of MEMS as handling thousands of volts and tens to hundreds of amps. Okay, so this is where we ended about maybe 10 years ago. We did this work. And it set the stage for the next project that I want to tell you about, which is now on the other extreme of the power range. And, lessons learned. I should point out some lessons learned here. My apologies for not doing that. The most important lesson to me was that the home contact theory, which treats the metal contact as a continuum, holds on the MEMS scale, as well as it does hold on the large scale. The second most important lesson learned from this was that, of course, the silicon version of the residential circuit breaker actually might work. But the third most important takeaway from this work is that of all of the parts in the relay that are difficult, it's, as you might imagine, the contacts that are most difficult. And that realization informs our next project, which I'd like to tell you about now. Okay, so the next project is still ongoing. It's to develop NEMS logic switches to compete with transistors. And it's supported by the National Science Foundation under the Energy Efficient Electronic Sciences Center, which is headquartered at University of California at Berkeley. So why do we want to do this? We want to compete with silicon in an effort to develop low energy switching technologies to reduce power dissipated in digital logic. And power dissipation ultimately, as you know, ends up in heat, and heat causes thermal management problems, serious thermal management problems if you've put your laptop on your lap. And it also results for poor battery life for handheld devices, the losses in digital electronic circuits do. So for those two reasons, eliminating heat and extending battery life, we would like lower energy switching from our digital logic. Now, if you think about where this loss comes from, it comes from two places. It comes from a dynamic loss and a static loss. And I'm trying to illustrate how that happens by this circuit here. Imagine that you have an inverter driving another inverter, and the two are connected by a wiring line. That wiring line has capacitance. There's also some gate-to-source capacitance probably in the CMOS logic in this gate, but in today's logic, the wiring actually dominates the capacitance. That capacitor is charged and discharged every time this circuit is switched, so you lose 1 CV squared times the clock frequency multiplied by some alpha, which is the activation frequency of the particular logic. It might be about 10% of the time that logic line is typically switched. On top of that, there is a leakage inevitably in the CMOS logic, and I'll come back to that in a moment. That leakage times the power supply is another source of loss. So this is a dynamic loss associated with how quickly you're switching. This is a static loss associated with just existing. And note that both of them are voltage dependent. Well, if you look at this expression here, you'll see that probably the easiest way to get low loss switching is to reduce the voltage. But reducing the voltage can only take you so far in CMOS. And I've tried to show over here the progression of power supply voltage as a function of time. You'll notice that somewhere around the mid-1990s, largely pushed by power dissipation. There was a push to drop the power supply voltage of computers, but it's beginning to flatten out. It's beginning to flatten out by around about 0.5 volt. That's about as far as the CMOS technology, I think, can go for a couple of reasons. First of all, if you reduce the voltage, then you are reducing your ability to turn the transistor off. At 60 millivolts per decade, you need, if you want to have logic that's got, say, 6 decades of on to off current so that there is no leakage current in the off state, and that's 6 orders of magnitude is roughly what it takes, you need 6 times 60 millivolts, or 360 millivolts, to turn that transistor off. Well, you're not going to get that from a power supply that's below 0.5 volt. So there's this sort of bottom range. In addition, there's also a push with these lower voltages to make the gates thinner, and that's because you need an adequate field strength to turn the transistor off. And if you're reducing the voltage, then you need to thin the gate oxide in order to keep that field strength up. And as you thin that oxide, it's going to begin to leak by tunneling. And so this static loss is going to go up. So as you try and drop the voltage of the power supply in the traditional CMOS logic, you're going to run into one of these two losses. Okay, so the question becomes then, can NEMS relays help? And now I'm thinking of a nanoscale relay because we'd like many of them per unit area. And I think the answer is yes, and I'm trying to convince you of that for 2 reasons. One is a relay, if it's really got an open circuit, it won't have this leakage. So we can get rid of this leakage and then focus on this term right here and ask the question is, what's the smallest voltage you could use to make a relay contact open and close? Well, there's no obvious physical limitation to that, like a 60 millivolt per decade rule. So maybe we can get below 0.5 volt this way. And if we can, then we're competitive. Up to a point, and I'll come back to that up to a point in a bit. And there are a lot of people who actually believe in this. I've just picked 6 pictures of different relays from work being done across the world. There are many, many, many groups trying to make electrostatically actuated relays for exactly this purpose, competing with transistors. And here are some of them. And the work has actually been quite successful enough to build an entire computer out of these relays. This is from a Berkeley, Tsu-Jae King's group at Berkeley. And there's, I think, on the order of 1,000 relays in this computer, and it's an 8-bit bus architecture. I think there's an 8 by 8-bit multiplier in here somewhere, up here, I believe. And so a lot of progress is being made, but unfortunately, these relays and the ones on the previous page, they're still switching at around 10 volts, or at least they were at the time of the publication. They're improving as well. But at the time of the publications, they're still switching around 10 volts. With the traditional wiring capacitance, that's going to be a lot of loss. So what we wondered is if there was another way to build these relays. And I think the answer is yes. Now, before I describe to you how we're going to build a competitive relay, I need to tell you one other thing about relays themselves. Relays are slow. You're using F equals MA to move a crossbar or something from an off state to an on state. And we're never going to compete with a gigahertz processor if we're moving mechanical parts around. So it's time to go back 100 years and look at how relay computers were built when they were just electromagnetic relays. What the builders understood back then is that you shouldn't build a computer the way we build computers today. Computers today are built with stages of CMOS circuits where you might have 10 or 20 gate delays, and each gate delay is 1 or 2 nanoseconds, maybe 5 nanoseconds. You add it up, and it's not a whole lot of time, and you can imagine a pipeline structure in which you're operating at gigahertz and beyond. To do that with a mechanical relay would be stacking up 10 to 20 mechanical delays, which could be much, much longer. And that time would be prohibitive from a computational viewpoint. So what the builders, what the designers of relay logic did a long time ago was to recognize that in no part of the computer should there be more than one mechanical delay. And what I've done is to take this AND gate here, which has, in the traditional implementation, 4 transistors here, 2 transistors here, 6 transistors total in 2 gate delays, and recast that in terms of a relay logic which has 4 relays here, and from inputs to outputs has only one relay gate delay. So from an input, which is this signal right here, or this signal right here, or this signal right here, to the output, from all of those paths, you would need go through only one gate delay, and if you go through 2, they're acting in parallel. In no place in this circuit is one gate driving another. I guess that's what I'm really trying to say. So there is a different topology if you're using relays that you should use over the traditional topology of the CMOS circuits. Now there's a small detail here, and that is, whereas the transistors here are 3 terminal devices, the relays have to be 4 terminals. You need to be able to separate the control inputs from the actuated inputs, because one of these 2 ends is going to be moving up and down in voltage. And if it's moving up and down in voltage and you have referenced the control to that, you're going to inadvertently change a 1 to a 0 or 0 to 1 if you switch that relay. So the relay inputs have to be independent, and that's why 4 terminals are required. So I have to keep this in the back of our mind when we design a relay for a high-speed relay switching logic. Okay, now here's my story about how to design a relay. Let's suppose you wanted to build a traditional relay, which is the type of relays that I had shown a little bit earlier. You might build a structure that looks like this, which is a 3-terminal device, and ultimately this cantilevered beam here is going to bend down and touch this and close a contact and make a path through here when a voltage is applied across these 2 terminals. So if I do that, you'll see then the beam bending down and making the contact. We learned this long ago. Anytime you have a contact between one part of a relay and another, you're going to inevitably have stiction. And on the micro scale, you can overcome that if you have hundreds of volts to use for actuation. On the nanoscale, when you're trying to actuate with subvolts, you have no force to work with. And here's the reason why. The moment you have contact, you will have stiction. In our case, it's probably not contact softening, but it's van der Waals forces, just the atomic forces between proximate materials. That stiction is going to require a strong spring to open it. Well, if you have a strong spring to break that stiction, then you need an even stronger actuator to close that spring to turn the relay to the other side. So if you have to suffer stiction, then you're going to require a large voltage. And it doesn't take a whole lot of analysis to realize that a relay built with sort of this fundamental flaw in it is not going to offer for low voltage switching. So we needed a different approach. And here's our approach. The relays that we build are nanomechanically fabricated, self-assembled. It was sort of mixing a top-down and a bottom-up fabrication approach. Top-down means I'm going to use sort of MEMS technology to fabricate large-scale features, and then bottom-up means I might use self-assembly of molecules to assemble small features. And here's the picture of our relay here, and I've labeled it as you might a MOSFET. Imagine that you have 4 electrodes arrayed across the bottom of a substrate here, built with top-down fabrication. And then, on top of them, using a self-assembly technique in which the molecules would be attracted only to the gold, and I'll show you how we do that. You get them to stand up on end here, and then you place a bar across the top. And the distances are important. This distance here might be on the order of 4 nanometers. This distance here might be on the order of 2 nanometers. Now, the 4 nanometers is important because at 4 nanometers, you won't get any tunneling current across this gap, and you won't get any tunneling current across that gap. On the other hand, if you apply a voltage between the 2 gates right here, and you create then a field, electric field, that goes around like this. You will attract and pull down the top electrode until such point as you sort of crush the molecules in the interior. And then, maybe it is that you can make the gap shrink to 2 millimeters here, and now tunneling is possible. And so we conduct, our relays conduct through tunneling, not through contact, importantly, so we don't suffer the stiction that you would in a contact relay. Furthermore, by crushing these molecules in the center, we actually prevent the contact. This is as far as one can go. And we keep the gates here recessed, so we have 4 nanometers, and the tunneling of the gates can't occur. And so these are some of the features which we feel are important. In the off state, there's no tunneling. In the on state, there is tunneling. And importantly, the molecular layer here, our original molecules that we grow, which we can buy or fabricate with very precise dimensions, are what controls the actual gap separation. We don't have to do it with unreliable fabrication. We do it with very reliable chemistry. Okay, and here's a little bit of physics to show you why we might be interested in this. What I've done is taken the Simmons tunneling model right here, and here's the original reference. An application of it, tunneling through through alkanes is shown in Ackerman's paper here, and repeated the tunneling response. This is on the side the current density, I think at 1 volt across the gap as a function of the gap width. And you can see that if you change the tunneling gap from 4 nanometers down to 2 nanometers, you affect almost 8 orders of magnitude, or a little bit less than 8 orders of magnitude of tunneling current. That's much more than the 10 to the 6th that we need in order to have a good on state and a good off state to keep the leakage current down and the static loss low. And so this is what makes us believe that we can build a tunneling relay. And I've got some of the switching trade-offs for typical design over here, and you can see that we're predicting on the order of, say, 10 nanosecond switching times, which, when multiplied by the factor of 10 that you might get if you use the relay logic approach, would be equivalent to a 1 nanosecond or a gigahertz processor. Here's the way we fabricate these devices. In a 2-terminal device. This 2-terminal device, we're going to apply voltage here across this and just look at the deflection and the current through it. This has all of the relevant physics so that we can study how the behavior works without going through the headaches of fabricating a 4-terminal device. We build our electrodes here. We use polyethylene glycol as the molecule because you can buy it in precise repeat units. With the thiols on the end, which stick to gold. So we're using covalent bonding to attract the gold, to stick the molecules only on the gold electrodes. And we build up a molecular carpet, if you will, that's somewhere around 3 or maybe 4 nanometers long, depending upon how many repeat units we have. And then we lay a graphene sheet across the top. And because we build a big mat like this, it doesn't really matter where we put the little graphene sheet. As long as we hit the electrodes, everything is good. And then, of course, if you apply voltage, we'll get a tunneling current, which we can measure through here. And here's the typical way that we would expect the forces to work. What I've shown is the 3 forces which are acting on this graphene sheet at the top. There's the elastic force pushing up of the molecules. There's the van der Waals force of attraction pulling down. And there's the force of electrostatic attraction. So the blue line is just the van der Waals, and the green is the compressing force of the molecule. And it spring hardens. As you fold that molecule up and begin to crush it, it pushes back with more vigor. And so the curve here bends up. If you forget the electrostatic force for a moment, you build it, and the deflection might be here, and then the van der Waals forces pull it into about there. Then if you apply the electric force, the blue curve moves up to van der Waals plus electric right here, and this operating point slides up to there. And we're able to compress in this particular design from about 3 1/4 down to a little bit less than 2 nanometers. And here it is in action. I don't know if you can see it, but there's a couple of traces On this one in particular, we go up and come down and go up and come down a couple of times. And so these are 3 different devices. The Simmons tunneling model plus the compression model with all of the forces is the solid curve right here. And the very good fit between the data and the solid curves indicates to us that we've got the mechanics correct and we've got the tunneling correct. And from this, we can pull out some of the material properties. So for example, we've pulled out the fact that the PEG molecules should be mechanical modulus of 15 megapascals. And if you go look it up in the literature, you'll find that PEG monolayers, which are about the only ones that have been studied, actually are around 15 to 20 megapascals. So we think we've got this right. Okay, and we had at least in this picture 5.5 orders of magnitude, and this saturation up here is due to power supply compliance. It could go up to 8 for all I know. All right, so future work. The first thing we have to do is to develop the molecules that are required for getting the force displacement characteristics just perfect so that we can bring that red line down onto the blue line and sneak the molecular force in there so that we can move with a much lower actuation voltage from 4 nanometers to 2 nanometers. And then we're headed, well, some nanofabrication advances to improve higher yield. Always want to do that. And then we're off to 4-terminal devices and circuits. But I'll tell you that we've actually gone and done some of this. Here are the results of a 4-terminal device. The only reason why I'm not focusing on it in great detail here is that we haven't published it yet, but I'm happy to show you the results. This is a gate voltage now being shown with a constant drain to source voltage and the tunneling current that we're seeing along the drain to source path. So here is a working 4-terminal device. Again, I don't know how many orders of magnitude we've got up here. We don't want to heat them up and blow them out before we've built them into circuits, so we're limiting the current to a few tens of nanoamps, microamps. But my suspicion is that this goes up to about the 10 to the minus 2 that we have seen as well, because it's the same tunneling gap, so why shouldn't it? But importantly, this is now controlled with independent gates. And again, it goes up and it comes down, it goes up and it comes down along the same path. So it's not sticking. We don't see the hysteresis that you would characteristically see of contact stiction for mechanical relays. And I'll just end with a comment about where do I think these devices could actually work. I'm not going to tell you that they will replace CMOS in laptops in the future, but rather I think there are 3 areas in which they could have a significant future. The first is autonomous personal devices. Those are devices which are run off of batteries that don't require huge amounts of processing. So battery lifetime is much more important than computation speed. You're not going to need multiple gigahertz for a Fitbit to record your heart rate. You just take that data and send it off to the cloud and let something else do the computing. You'd much rather have never replace the battery. Similar statement would be for autonomous sensor nodes that are maybe powered by energy harvesters, which have limited capability. Most of the time they're off. I'm trying to show that these stations here are off, and a few of them are just communicating along a chain back to the base station. So for such intermittent processing, even if it's a decent amount of processing, but for a very small amount of time, this is another case where power overrides computation speed. This might be a good application. And finally, the power switches that are in logic blocks today are typically implemented with PMOS transistors that are leaky. Now, they don't turn on and off all that quickly. The operation might be a gigahertz for the computation, but computation blocks can be switched off for much longer periods of time and then turned on for much longer periods of time. So if our relays don't leak, this might be a good application as well. You could tolerate a sort of 1 or 10th gigahertz switching of a computation block just so long as it didn't drain the battery when it was turned off. Now, if all of this sounds crazy to you, I'll just remind you of one thing. Here's a picture of what the very first transistor looked like at Bell Labs. It's kind of got a conductor suspended by a spring over a germanium contact, and it looks like there's no possible way in the world that this could act as a transistor. And yet, give it 68 years, and this is what it looks like. So, whoops, excuse me, what did I just do? Right. Give us the same 68 years and our graphene sheet suspended above a molecular spring might actually be integrated into a low energy switching computation network. Anyway, so my example of a very high power MEMS relay, probably higher power than you might have thought that MEMS could be, to a very low power relay, maybe very much lower than what you might have thought a NEMS relay could process. And there's obviously a lot of room in the middle as well. So with that, I'll end and entertain any questions if you have them.
So do we have questions? Thank you so much, Jeff. I see one there.
Hello. What sort of problems are there with fatigue in regards to failure? So like the arm breaking after so many switching cycles?
So silicon is a wonderful material. It does not fatigue. It's brittle. So if you keep within its fracture stress of a couple hundred megapascals, perhaps, some people push it a little bit higher if you've got very nice, shiny, etched walls, it won't fatigue. If it fails catastrophically as a fracture. So fatigue is not a problem. It's one of the very nice features of silicon.
Okay, a few more questions. Why don't we
Yes, I have a question. So you talk about like high power is about like 3 amp, that is high current. Can we go even higher than that, like 3,000 amp?
3,000 amps. Well, I'm prepared to say that we can get to the 2 newtons, which permits the 10 to 20 to 30 amps continuous conduction. On a MEMS device, I'm not sure I would want to promise the thousands. I will point out, though, that the 10,000 amp surge comes with a sort of an I squared T limit. What's really important there is the thermal energy that you deliver into the resistance. So I squared R, the power dissipated, times T. You can survive that 10 to the 4th amps as long as T is very short, which is why the magnetic actuation is used to snap open the residential circuit breaker. That acts extremely quickly, so the integral of I squared T is very small. It's conceivable that our relays could also withstand that with a very fast-acting sensor, but not for a long period of time. Oh.
Okay, I just first want to thank you for the great talk. So I have a little technical questions about the last device that you presented, where you use like a self-assembled polymers or molecules to control the distance. I'm just curious, like how do you precisely place the same amount? I assume that you use a symmetrical amount of polymers or molecules on both ends, so that because I'm just wondering if you have different amount of molecules on different end, when they apply with a different voltage, will that cause different gap distance on the source and drain? So it gives you a different current on both sides.
I'll answer 2 questions, the one you didn't ask and the one you did ask. The one you didn't ask was, how do we know that the molecules are all the same length when we put them down, and so maybe they have a distribution of high to low and they tip or something like that. Therein, we rely on the chemists who are extraordinarily good at giving us a solution of just 22 repeat units or just 30 repeat units. As for the density, right now we use time. We do this self-assembly in a wet solution, and we wait long enough so that by spectroscopy across the surface, we can actually measure out what we believe is the density of molecules. We just simply wait long enough for the chemical reaction to fully populate all of the areas. I'm not saying that that's adequate for a production facility, but that's what we're doing now.
So for your NEMS device, it looks like it's normally in an off state, and then you apply a voltage and it turns on.
Yep.
Can you do, or do there exist molecules that can do the opposite, so that it's normally in an off state, on state, and then you apply a bias and it turns off?
Actually, yes. There are electrically active molecules wherein you inject an electron into a molecule and it will change its conformation. Most of the ones that I'm familiar with fold, but I'm going to guess that there are some that unfold. So that would be a possible answer to your, a positive answer to your question. In this case, I would defer to my chemistry partners to bear me out, but I'm going to take a guess and say yes.
Do we have one more question? We have a mic.
Hi, thanks. This is kind of a silly question, but if you were to build a large mechanical switching device to do some sort of complicated logic, do you think you'd ever have to worry about sort of coherence of motion? So if you have all of the switches moving coherently, then you have the center of mass moving, and so the object would vibrate.
Well, that's an interesting question. My guess is that the substrate on which we build this would be sufficiently massive so that that wouldn't happen. I can't say we've studied it, but the substrate is considerably more massive than any of the moving parts. So I'm going to take a guess and say no. And furthermore, I can tell you that the traditional shock test of 10 to the 4th Gs or something like that wouldn't move the crossbar on our membranes. They are so light in comparison to the stiffness of the molecular springs that shock wouldn't cause a relay to open or close. So we've done that math.
Okay, great. Do we have any more question? One more question.
Get your exercise, Regent.
That's fine.
Thank you for that very nice presentation. With the several orders of magnitude of change with the amount of current that can flow through the tunneling, do you think there's an opportunity for a tri-logic device?
Oh, well, okay. So I think there's an opportunity to use it as a continuous valve. So why not build an amplifier out of it? And having said that, I guess I have to answer yes to your question that you could have a tri-logic device. The devices that I showed you don't necessarily pull in. If you were precise enough with your gate voltage, I think you can actually sit in the center. So you could have multiple levels of conduction.
Thank you.
Okay, any more last question? Then I will wrap this up. Perfect. Thank you so much. We have one more. Okay, this is the last one. You guys are oscillating like this.
Thank you so much. So I was wondering that other than from a legal standpoint, what would be the advantage of MEMS circuit breakers over solid-state circuit breakers?
None. No, leakage. Leakage would be the only one. So I don't know if you noticed it, but Packard Electric was one of our sponsors long ago when we did this work. And they're an automotive company. There are thousands of transistors in an automobile controlling many electromechanical devices. And we tried probably for 10 years running to beat MOSFETs. And every time we caught up with the MOSFET, it went ahead by another decade. And so I would say that it is almost impossible for relays of our flavor to compete with purely solid-state switching. You could make it work, as we've shown, but from an economics viewpoint, with the huge automotive market and other power semiconductor markets, I don't think we could compete economically at all. So it's really the requirement for the open state air gap that gives us our entry. Otherwise, the residential circuit breaker, which I showed you, wouldn't exist as well. For non-residential settings, some non-residential industrial settings don't have to have an open gap, some. And there, it's all solid-state circuit breakers. I think that's the telling answer.
Thank you so much, Jeff.